Today we are going to explore derivatives and the fundamentals of what a derivative is in limit notation. So on the screen right now is the formal definition of the limit, as many of you have already learned, where we increment f of x by a small amount h, subtract that by the original value, and divide that by the small increment h. And we know that this is the equivalent to the secant line, and as we take the limit as h approaches 0, we are taking that secant line between the 2 points, and the 2 points are coming closer and closer together, and as it approaches 0 it forms a tangent line. So this is the original thinking behind the derivative, but there's also another way to visualize it, and it's easier to compute while maintaining the same steps. So I'm first going to run through an example to show you another way of thinking about it. So let's take a function, let's call it y, and let's set that equal to 2x. So we know when we're taking the derivative, we are measuring the increment change in y versus the change in x. So let's represent this with deltas. And if you don't know what delta means, it basically means change. So y plus the change in y equals 2 times, and this is important, it's in the parentheses, x plus the change in x, delta x. And what we're looking for is to find a way that we can relate the change in y to change in x to a certain equation. And in order to reach this, I'm going to further simplify the equation. And being the algebra students we see a clear relationship between knowing that y equals 2x. So we know that two variables are equal to each other. So we could just eliminate those two variables by subtracting y and 2x, because you know it's going to maintain equality. So we can reduce the change in y to 2 times delta x. And so now we already are beginning to see a relationship between the change in delta x and the change in y. So in order to make it an explicit function of the derivative, we can just turn it into the formal form that we saw earlier, where we saw a change in y over the change in x. So what we could do is do this by dividing by delta x on both sides. So we could do delta y over delta x, and this is going to leave 2. Now, you might think we're done already, but we're not. So while it's already matching what the power rule says and the formal definition of the limit says, we still have to take the limit as delta x approaches 0. And this is because we want the point of tangency, not exactly any delta x or delta y. But lucky for us, as we take delta x equals 0, it still equals 2, which is not always the case. So let's go do another example. So what's important to know about the previous example is that we are not changing the way to think about the derivative, but we are only merely visualizing it and solving it in a different way. So let's make a function y and set that equal to x squared. And for a change in x, there is a change in y, and we are measuring that relationship and change between delta y and delta x. So we'll add delta y to the left and delta x to the right. And we'll algebraically expand it. Then we will use our equality up there to simplify this algebraically. So we know y equals x squared, so we can subtract that from both sides to get a clear relationship between delta y and delta x. And this will end up in delta y equaling 2x delta x plus delta x squared. Like the previous example, we want this to resemble the ratio between the change in y and change in x. And to do this, we can divide by delta x. And this will end up equaling 2x plus delta x. So now we have that. Let's take the limit of delta y over delta x to form a tangent line as delta x approaches 0. And delta x, as it approaches 0, it cancels out this delta x term, so we're left with 2x, which we know is the derivative of x squared. So what I drew on the grid lines is the same example as the one from before, but with the diagram, to understand what we're actually doing with the processes that we're doing. So I guess it's best to start off with, we're adding delta x and delta y at the beginning of each step. So what is that truly doing when solving for the derivative? Well, if we look at the function on a more miniature scale, well, let's say it goes like this. There's merely a delta y represented by the green. Of course, this is a much larger change than what happens in the derivative, and then delta x represented by the blue. And what we're doing is just creating that difference where we're adding a delta y to the function, a delta x to the function, and seeing how it responds. And then once we do that, we do elimination by getting rid of the y variable, and this is to solve for delta y. And from there we do delta y over delta x. So this one, let me write this down, plus delta y plus delta x. That's what we're doing here. So the next step we're doing for that same parabola is that we are just finding the relationship between this. So let's say it goes up like this. We could say green equals 2 blue. That's the change in the green one with respect to the change in x. It'd actually be a negative, by the way, in this case. But so we're just measuring the ratio between the change in x and the change in y. And the final step, where we take the limit as delta x approaches 0, all we're doing is taking the same parabola but going from these very large changes in change in x and change in y and making them super small, like that. So, and when we make it small enough, we can represent it with the line, a tangent line, which represents the slope at that point, the instantaneous slope. And we can just draw the line. And you can also draw lines for the other ones, except they're just not accurate representations of what's happening. That would cut through that because these are secant lines. But since we keep on taking delta x as it approaches 0, of delta y over delta x becomes a tangent line.